Hello to all of you, and I send greetings in the name of Jesus Christ our Lord. My name is Marcus Ross, and I'm a paleontologist living in Virginia. I have the distinct honor and privilege to be part of your meeting this year, and I'm very grateful for it. I have also had the distinct honor and privilege of visiting your wonderful country several years ago as I worked on my PhD dissertation on a group of animals well known from the Netherlands, and that is the Mosasaurs, a group of which I will be speaking and talking about today. The title for today's talk is Of Mosasaurs and Meteors, Life and Death in Noah's Flood. So the structure of the talk here today is going to follow four different parts. First, we will have a long look at the biology of these most amazing marine creatures. Next, we will take a look at their distribution in the rocks of the world, the sedimentary rocks of the world. We'll then take a look at issues regarding their extinction and also a question about their extinction during Noah's flood. So, our first area of exploration is going to be in mosasaur biology. What were these creatures? How did they live? Where did they live? Mosasaurs were magnificent. They are fully marine lepidosaurs. That's a fancy word for lizards. The group that includes lizards and snakes is known as lepidosaurs, and mosasaurs fit very nicely within the groups that we usually consider as lizards and snakes. So, while dinosaurs are a very different sort of organism that is more similar to crocodiles and in other ways more similar to birds, mosasaurs were much more similar to snakes and lizards that we have alive today. They were, however, much larger than virtually all of the snakes and lizards that are alive today, because these animals were on the small side about 3 meters long, and on the long side, in fact, the very largest of the mosasaurs known is from the Netherlands, a specimen of Mosasaurus hoffmanni, clocking in at 17 meters in length, 54 feet for we Americans over here. So these creatures were enormous, and they were also beautifully designed for life out in the open ocean. This illustration from paleo artist Mr. Hawley shows 3 different species of mosasaurs known from North America. Tylosaurus prorigor towards the bottom. In the middle, Platycarpus tympaniticus, a medium-sized mosasaur of about 20 feet, about 7 meters, and then Clydastes liodontus, which could be anywhere from about the 4 to 6 meter side of things. These animals, you'll note, have long tails. They have paddles and flippers instead of hands, and their bodies are extraordinarily streamlined with a very large head filled with a lot of very dangerous and pointy teeth towards the front. Most of the mosasaurs were generalist predators. That is, they would eat whatever animals happened to be in their way and available at the time. Something like Tylosaurus would eat a wide variety of different fish, reptiles, and other creatures. Some of the mosasaurs, however, were much more specialized. As we'll encounter, some of them were what we call durophagous, which is a fancy word for they ate shells, harder shells such as clams. Others would eat only fish, or seem to be eating only fish. We refer to them as being piscivorous. Now, mosasaurs, as I mentioned, were variable in size, but all were rather large, 3 to 17 meters in length. The average size of a mosasaur was probably somewhere around 6 to 7 meters, with a few species that got to be very, very large and a number of them that were on the smaller side. Currently, there are about 40 valid mosasaur genera. You might recall that the genus that we belong to is Homo, and our species is sapiens, Homo sapiens. So when we're talking about mosasaurs and I discussed their genera, I'm talking about the larger name that may have anywhere between 1 and up to 6 or 7 different species inside them. So there were more species of mosasaurs than genera, but the genus is easier to talk about because the genus is rather typical and easy to identify from fossils, whereas the species requires very specific kinds of bones often in order for us to be certain of that assignment. So in paleontology, sometimes it's a lot easier to talk about these animals by the larger group that we call the genus. So let's take a look at a few of the 40 different mosasaurs that are out there. Here is an illustration done by paleo artist Dan Varner of Tylosaurus. Tylosaurus was a very widespread mosasaur known from North America, from Europe, all the way over to New Zealand. And Tylosaurus, from a specimen discovered in South Dakota, where I did my master's degree in paleontology, is illustrated here hunting a swimming marine bird called Hesperornis. And that's because from one of the specimens discovered in the 1980s, there was a Tylosaurus that had the remains of that bird inside its stomach area, along with the remains of a few other things as well. At least 2 different species of fish, a couple of different shark teeth were found alongside it as well, and the bones of another species of mosasaur. The mosasaurs do not appear to be cannibals, but they might not have objected to eating a close cousin. Tylosaurus would be one of our generalist predators and could be upwards of over 14 meters in some cases. Another generalist predator is this animal, beautifully illustrated here again by Dan Varner, of Plioplatycarpus. This is a Upper Cretaceous, Late Cretaceous, and Maastrichtian member. Also had a very global distribution, found all over the world, and illustrated here giving birth to its young, which is something that we now know mosasaurs were able to do. Now, again, mosasaurs were lizards. They were not mammals, and so they do not have a placenta. They do not nurse their babies with milk, but instead, the egg of a mosasaur would stay inside the body cavity of the female, and the embryo would grow inside that egg. The shell would have likely dissolved, and then the egg would have been passed out of the body where the baby emerges, grown at least enough to handle life on its own. We don't believe that mosasaurs did much for parental care. We certainly don't see very much parental care in lizards and snakes. So mosasaurs are known to give birth to their young live, much like some of the other marine reptiles, such as ichthyosaurs and plesiosaurs. One of the more specialized mosasaurs that we know in the fossil record is this animal, Plotosaurus. This is one of the piscivorous types of mosasaurs that we believe was eating only fish, as opposed to something like Tylosaurus, which was eating anything that it wanted. Plotosaurus has got a very long body compared to some of the others, very streamlined with a very thin, long head, and the tail. Now, one of the things we've discovered now about the tail, paleontologist Johan Lindgren from Sweden initially discovered that the tail of Plotosaurus actually was curved downward. So this earlier illustration is somewhat inaccurate. The lower part, back end of the tail would have curved downward and would have created a fin with an upper support structure as well. Also notice, as we take a look at the hand, that the forward flipper has many, many bones for the fingers. You and I each have 3 fingers in our hand, each of our fingers, aside from the thumb. There's just 2 there. But for Plotosaurus, it exhibits a condition that we call hyperphalangy, which is a fancy word for saying lots of fingers. And as a result, when we take a look at the animal over here, we find that Plotosaurus was probably a fast pursuit mosasaur. Fast pursuit mosasaur. So rather than being an ambush predator, like most of the mosasaurs were, this one instead is going to be chasing after fish out in the ocean. Another of the very specialized mosasaurs is Globidens. Globidens has a distribution primarily in North America and in northern Africa. It's known from Alabama and South Dakota, but most of the fossils of Globidens are now coming from Morocco. Globidens has very large, almost onion-shaped teeth in the back designed for crushing shells. The front teeth are kind of thin and more rake-like so that it could scrape through the sediment to pick up the clams and then crush them with the back teeth. Globidens was a smaller mosasaur, typically only about 5 or 6 meters in length, but the skull was very heavily constructed to reinforce for the strength necessary to break these clams. There are a few other mosasaurs that were eating hard-shelled materials, the animals that we call being durophagous, shell crushing. The Netherlands is home to one of the more unusual ones in the form of the small mosasaur Carinodens, only about 4 meters in length, and Carinodens' teeth, rather than ball-shaped, were long, thick blades that were capable of crushing things like shrimp rather easily. And the work of Dutch paleontologist Anna Schulp does a nice job of illustrating some of the capabilities of that animal. Now, my evolutionary colleagues, such as Anna Schulp and other mosasaur workers, believe that mosasaurs evolved from a previous group of terrestrial animals that eventually migrated their way into the streams and lakes and oceans to become marine organisms. In order to trace those relationships, which they believe happened via evolution, one must construct an evolutionary tree. The way this is done is by studying in great detail the anatomy of the animals and measuring the bones, identifying which ones are there, their relationship to one another, and other sorts of features that can be codified and placed in a number-based data set that we call a character matrix. Now, when we think of how to identify animals, sometimes we just look at an animal and we say, oh yes, we know that's a cat, yes, we know that's a horse, and those sorts of things. Paleontologists can also easily recognize from the skeleton the basic group into which an organism belongs, but when it comes to trying to identify or name a species, I want you to get a feel for just how specific our evaluation and our study of these animals are. A typical character matrix that would be used for one of these evolutionary tree diagrams might include over 100 different characters, possibly 200. For example, some of these characters might be things like the number of teeth in the dentary, that is the lower jawbone. How many teeth are found, because this may vary from one species to another. The position of the pineal foramen along the frontoparietal suture. That is a complicated phrase. The pineal foramen, if we think of a mosasaur skull and we tip it so we're looking on top of the skull itself, has a small hole in the very middle on the top of the skull. That is called the pineal foramen. That pineal foramen is found either within or alongside one of two bones. The parietal bone, which is on the very top of the head, and the frontal bone, which is a little bit further towards the front of the animal. The pineal foramen, if we tip that skull and we're looking, is almost always inside the parietal bone, but sometimes it's in the middle of the parietal bone, sometimes it's near its connection to the frontal bone, and other times the pineal foramen is actually a hole right along the connection between the frontal and parietal bone. There's a little hole right in the middle. That's a very specific type of observation, and it's important for understanding what these animals are and how they differ from one another. Other things might be things like the quadrate stapedial pit shape. The quadrate is the bone that acts as a hinge between the lower jaw and the upper part of the skull. So mosasaur jaws are a simple hinge, and the quadrate is that hinge. The stapes, an ear bone, comes in direct contact with the quadrate, and there's a little hole where the stapes fits. So what is the shape of the stapedial pit, hole where the stapes fits? This is not something that most of us would look at a skeleton in a museum and recognize and identify. We're not trained for that, but others of us are. And something like the vertebral condyle shape. Our own backbones have, they're vertebrae. The condyle is the point of connection to the next one, and in mosasaurs there is a ball and a cup. And the condyle shape? Is that perfectly round? Is it taller than it is wide? Is it wider than it is tall? How deep is the cup? Those sorts of questions are things that mosasaur experts and other paleontologists are going to be looking at in order to code and classify the characters and put them into this large data matrix. And there we end up producing a tree-like diagram if you believe that evolution is true. So here are 4 different examples of evolutionary tree diagrams done by the same authors in the same paper. So several different cladograms, these evolutionary diagrams, all with certain points of agreement, but also differing in agreement. And these are 4 of about 8 or 9 possible cladograms that were produced by these authors in this one paper. This is Simos and other authors, published in 2017. And I put this up here not so that we can evaluate it, but rather to recognize that when an evolutionist produces a evolutionary diagram, the characters that they have selected are put into a computer program that will make a tree. In fact, it will make hundreds of trees. Those are the only types of diagrams they can make. They can only make trees. So a cladogram doesn't prove evolution. A cladogram assumes evolution. And moreover, lots of cladograms are equally valid mathematically. And so the researcher is then left to try to decide which style of cladogram, which rules by which they evaluated their data matrix seem to make the most sense. So there's a certain objectivity to the study. Do the bones exist? Is the hole in a certain place or not? How many teeth are in the dentary? But then there's also a certain level of subjectivity in which the researcher has to try to decide, does this computer program result seem to make sense? I don't agree with evolutionary theory, but I do find that these diagrams can be somewhat useful in trying to understand whether animals are fairly closely related to one another or if they're very separate from one another. But as a creation researcher, I would prefer a different approach. So, for example, I can take the same data set that has all of those different characters and analyze them using different kinds of programs that are not going to make evolutionary trees. Rather, we can evaluate them with different types of programs that can make cluster diagrams that will show us whether animals are close to or far away from one another. And hopefully, with these types of diagrams, we can get a sense for which mosasaurs might actually be part of the same created kind. Another term might be basic type, as used by some of my colleagues in Europe. But whether you call them created kinds or basic types, what we're trying to do is figure out what are the types of organisms that God initially created, or organisms that were alive that were part of their original created kind at the time of Noah's flood when these fossils were formed. Here is an evaluation that I did quite a number of years ago of the mosasaurs from the standpoint of created kinds. And when we took the data set that was available back then and ran it through our evaluation programs, what we discovered is that the mosasaurs clustered into at least 2 groups and possibly 3. We had the mosasaurine mosasaurs, such as globidens, Mosasaurus, Promathodon, Clydastes, and others, and the russellosaurine mosasaurs, such as Tylosaurus and Plioplatycarpus that we saw earlier. And then there were a couple of other mosasaurs, such as what are called the halisaurines, Halisaurus, Russellosaurus, for example, that may or may not be a group of their own. We're not quite sure. So, like my evolutionary colleagues who are producing trees and considering those hypotheses, this cluster analysis is not the final word on mosasaur relationships, but it is a hypothesis about which groups belong to the same created kind. Now that we have looked at mosasaur biology in some detail and gotten a good feel for these amazing creatures, we're now going to look at what is called mosasaur biostratigraphy. The question that we need to ask first is, what is biostratigraphy? Well, biostratigraphy is about which animals are found in which layers of rock. Bio, of course, meaning life, and strata, meaning rock layers. So the animals found in rock layers. Now, even before that, we might ask the question, where on Earth are mosasaurs found? And the answer for that is actually quite a few places on Earth. This is a diagram I put together of the major mosasaur localities in the world. You will notice that there is a heavy concentration in Europe and North America. That's not an accident. It is largely because paleontology began as a European endeavor and became very important in North America as well. And so those two areas have been very heavily studied by many, many researchers, especially Western Europe and all of the United States and Canada, for example. But there are also very important localities in places like Morocco. I mentioned that before, for example, with globidens, and many, many other mosasaurs are known from Morocco. There are even mosasaurs known from New Zealand, places like Bolivia and Brazil, even all the way down to Antarctica, and a number of locations in the Middle East. These are the places around the world in which marine Cretaceous rocks are well represented, and therefore mosasaurs who were swimming in the waters when these were deposited are well represented in these rocks. So if biostratigraphy is life in the rock layers, where are the mosasaurs known? As I mentioned, they are known in Cretaceous rocks. So where are those? Well, first we take a look at a basic geological column, including the Paleozoic, Mesozoic, and Cenozoic. Those are the main fossil-bearing rocks of the world. The Proterozoic has some fossils as well, but not much for the large-scale types of fossils. It is in the Paleozoic that we begin seeing many different types of shelled animals and fish. The Mesozoic is famous for dinosaurs, and the Cenozoic is famous for various types of mammals. Now, as a young Earth creationist, I believe that at least the Paleozoic and the Mesozoic, along with some part of the Proterozoic at least, were formed during the flood. There is quite a bit of debate in creation circles about how much of the Cenozoic is flood versus how much of it is post-flood. I tend to think that the majority of the Cenozoic was formed after Noah's flood was over, when Noah released the animals and they left the ark, began to spread out over the world. Some of my colleagues disagree and believe that much of the Cenozoic was formed during the flood. That's a different fight for a different time, and it's one that we enjoy as colleagues in creation, sharpening each other and challenging each other within our models. Now, mosasaurs are found in Mesozoic rocks, which name means middle life. But within the Mesozoic, we have three divisions: the Triassic, the Jurassic, and the Cretaceous, and mosasaurs are not found in Triassic or Jurassic rocks. They are found in Cretaceous rocks, and moreover, they are found in the Upper Cretaceous rocks, in the bright green here, from rocks that are known by the name of Cenomanian up through Maastrichtian, a name that should sound very familiar for all of our friends listening in the Netherlands. So that is where mosasaurs are found in the rocks. Now we're going to take a look at an example of how to study mosasaur extinction, for example, which happens to occur at the end of the Cretaceous. We call this the K-PG boundary. K is the geologic designation for Cretaceous. PG is the designation for the Paleogene. And for my dissertation work at the University of Rhode Island, this was a significant part of my study. So going back to our map of the world, we're going to take a closer look at the mosasaurs that are known from New Jersey and Maryland along the United States East Coast, and the Netherlands and Belgium in Western Europe. And we're also going to take a look at some of the evidence for a large meteor impact that occurred at the end of the Cretaceous, the end of the deposition of Cretaceous rocks, and that impact in the Yucatan Peninsula of Mexico that we've heard that's supposed to have killed off all the dinosaurs. So, the state of New Jersey is along the east side of the United States, just south of New York City, and also next to the major city of Philadelphia, and so this is part of New Jersey. There are two localities that, which is a geologic term that we use for places, two localities of interest here. One is in a small town by the name of Sewell, and the other is actually a core section, a package of rock that was drilled up and out from a place called Bass River. At Sewell, there is a quarry, and they are mining material for fertilizers. And fortunately enough, there are a good number of fossils in that mining pit. And these are some of the geological names for the locations as far as the layers of rock. Geologists give names to various layers of rock, both locally as well as globally. And so in New Jersey, you have what is called the Navesink Formation. And on top of that, after a kind of an erosional gap, is the New Egypt Formation. And inside the New Egypt Formation is something called the MFL. That is the main fossiliferous layer. That's going to be important later. Over in nearby Maryland, which is close to Washington, D.C., is the Severn Formation, which is mostly equal to the New Egypt Formation. Here is a picture of the quarry in New Jersey, in Sewell, where the mining of material for phosphorus, for fertilizers, is done. And you can see a few people that are out and about, and they occasionally open the mine so that people can come and collect fossils. So mosasaurs have been found here, along with ammonites and turtles and sharks and other types of fish. A variety of different types of fossils have been found, many of them concentrated in that main fossiliferous layer. You can see a sharp distinction in color with the tan material, that is soil, and a little bit of sediment from much later deposits in the Cenozoic. So we have Cretaceous material down here. In Bass River, the area has been drilled and a core was removed. And what's important about that is that the same rock unit, the Navesink Formation, is found, and at the top of the Navesink Formation is a group of material, circle it here, group of material that was formed by an impact in Mexico, raining down small glass beads of superheated rock, laying down clays that were enriched with a material called iridium. And so some of these things are noted. Shocked minerals, these are things like quartz that have little lines on them that indicate that they were formed at very high pressures from a meteor impact. The glass beads are called spherules, and then there's some other strange sorts of materials in that. Over on the right side, you can see the word Cretaceous here and Tertiary. So the line between them represents the K and PG of our boundary. Over in the Netherlands, I had a great opportunity to visit the town of Maastricht and also others. I got to visit the Tylers Museum, for example, and see some of their wonderful classic materials recovered in the 17 and early 1800s. So, of course, Maastricht, the Highlands area to the far south, has a large number of formations. So, just like in New Jersey, we had the Navesink and the New Egypt Formation. In the Netherlands, you have the Gulpen Formation and the Maastricht Formation, and those formations are further subdivided into smaller units that we call members. And these can be seen at the NC Quarry, which is now closed as an operating quarry. It mined rock there, but is still occasionally open for visitors to come and look for fossils. So if you're ever in Maastricht, it would be great maybe for groups to get together and see if they could get a permit to go collect fossils in that area. And I had a chance to visit the NC Quarry, and also, a little hard to see, but you might be able to notice that there are some little black dots on the picture. These are historic caves. Before the quarry was made in the 20th century, the chalk of the Maastricht Formation was mined by tunnel mining. And I had an opportunity to actually go into these mines led on a tour so that we could see a Cretaceous-Tertiary boundary exposure that had been opened up by a ceiling collapse. So the roof of the mine in there had actually fallen down and exposed this. Here is a very similar system to what is seen in the Bass River core of New Jersey. Once again, we have a boundary that has a spike in the rare metal iridium, some very strange clays that are formed as particles are settling out, and there are even shocked quartz pieces that have been concentrated by burrows of shrimp. So the animals were here as everything fell down. The animals burrowed down and took some of the small shocked quartz material with them. So the same materials that we see at the top of the Cretaceous units in New Jersey are found at the top of the Cretaceous units in the Netherlands. This means that we should be recognizing this impact and the debris that fell down as a single event that occurred on both of these continents at a particular time during Noah's flood. When I looked at the mosasaurs that were found on both sides of the Atlantic, there were many similarities between them. In yellow are the mosasaurs that are known of the same genus on both sides and the same species on both sides. Animals like the shell-crushing carinodens, the more generalist Lyodon, Mosasaurus, and Pliopodicarpus. The genus Pronathodon is known on both sides, but from slightly different species, and Pronathodons seem to be going after turtles and larger prey. And then each continent has members that are not yet, at least, found on either side. In Belgium, Tylosaurus is known from the lower Maastrichtian, and in North America, Halisaurus is known from the upper Maastrichtian. So all of these are found below fairly similar Cretaceous-Paleogene boundaries. And there's no intact mosasaurs above those boundaries. So it seems like we have mosasaur fossils, an event, and no more intact original mosasaur fossils. We occasionally have some that were eroded and redeposited. So in my dissertation, I was approaching this from an evolutionary perspective, not from a creationist one, but I was always thinking about creationist applications as I did this. So what I used was a mathematical approach called rarefaction. Let me show you on the next slide what this really means. If we take a look at the rocks that are known from New Jersey, from Maryland, and from the area around Maastricht, for example, what we find is that there are lots of mosasaurs, but they are not evenly distributed amongst all of the different rocks. Some of the rocks, such as the Severn Formation, have very few mosasaurs that have been found, mostly because it's a very urban area and there's a lot of building on top of it. Very few places in which they've been mined out and found. The Netherlands has produced more mosasaur fossils, teeth and bones, than the North American ones. But North America has some well-described and well-known specimens as well. So what we need to do is find a way to unify different parts of this system. And I did so by creating 3 different bins in which we could take the mosasaurs of, say, the Navesink Formation and the Wieland member of the Gulpen Formation and put them together as a single bin. Likewise, we could take the New Egypt Formation, the Severn, and most of the rest of the Gulpen and Maastricht formations. And then the main fossiliferous layer at the very top of the New Egypt Formation connects very well with the Meersen member, and so everything that was found in those could be binned together. Now, even when that happens, we don't have an identical number of mosasaur fossils in each bin. Instead, what we have is the lower bin, bin 1, has 22 specimens represented by 5 genera, right over here. Bin 2 has many more fossils, 208, from 6 different genera. And bin 3, the uppermost bin, has 45 specimens representing 5 genera. And the question I wanted to ask was, is there a way in which we can compare these so that they are equal in some way? And the answer to that is a mathematical tool called rarefaction. It's used by biologists and also by paleontologists. What rarefaction does is say, well, what if we took the large groups, bin 2 and bin 3, and only sampled 22 of them? What would we expect the number of genera to be if I took a random grab out of the 208? And I found that mathematically I would expect a little more than 4 genera, on average about 4. And our variability to that, what we would use to figure out our range of possibilities, is this 0.9 down at the bottom. For bin number 3, the uppermost bin right below the KPG boundary, I found that we should also expect about 4 mosasaurs. So the fact that we actually have 5 at 45 means that we should have 4 if we sampled just 22. So it seems that the number of mosasaurs per bin, when we correct for a small sample number, is approximately equal. To put it in a graph form, we find our bin number 3 is at 5 over here, and our bins, actually this would be bin 1. I call them a little bit differently in my dissertation, but our first bin is at 5, our second bin is a little over 4, our third bin is a little over 4, and our range of possibilities are represented by the lines here. And so this tells us that, statistically speaking, there are equal numbers of mosasaurs in each one of these bins. Now, that is important because it tells us that it seems that mosasaur diversity was not changing at all as we go up through the section. So, what does this mean for our final analysis? Well, mosasaur fossils are found in sediments. They're found in sediments all around the world that were deposited when sea levels were very, very high. Places like South Dakota today are 1,000 to 3,000 feet above sea level in the places where mosasaurs are found. There are mountains that are higher than that, but the areas where the mosasaurs are found are 1,000 to 3,000 feet high. The water of the Atlantic Ocean and the Gulf of Mexico is thousands of miles away, many, many miles. And so there must be some way in which the ocean levels were high or the continents were low, or both, in order to get the continents flooded with water, which is something that we expect from the description in the Bible of Noah's flood. I think that the mosasaurs are being deposited, that they are being destroyed by catastrophe towards the end of the flood. We also, as we saw, see similar mosasaur faunas between both the East Coast and places like Maastricht and the Netherlands. So this is an area where similar mosasaur groups are towards the end of the flood. And we don't find any mosasaurs that seem to have been deposited after the KPG event, after the asteroid. So any mosasaur fossils that we find above that boundary usually look like they've been worn and broken. It's not complete skeletons, it might be occasionally a tooth, and teeth that are not in good condition. So we believe that those have been removed and reburied at some point. And there's very, very, very few of them. So it appears that the last appearance of the mosasaurs, the last time we find in-place mosasaurs, like full skeletons, is coincident with all of this impact-derived material, all of this evidence for an asteroid or meteor impact that occurred in Mexico. And it doesn't appear that the mosasaurs, they are dying, no doubt about it. Their bodies are being killed and their bodies are being deposited by sediment. But there doesn't seem to be any particular gradual die-off of the mosasaurs. It looks like they might almost have made it through the flood. And so I think that mosasaur extinction might not have actually been directly caused by the water component of the catastrophe. Mosasaurs were fairly strong swimmers. It seemed like they had been able to avoid much of the destruction of Noah's flood. But towards the later end of the flood, there was this impact. And that impact must have had a very negative situation that occurred to their ecology. What might that be? Well, some of the effects of that impact would have been what some people have referred to as being like a nuclear winter, in which there was a massive collapse of the food chain in the oceans. Mosasaurs were top predators. If we think of all the animals in the sea like a triangle, you have many plankton and single-celled algae at the bottom. Those algae feed a large number of grazers and small fish, which feed larger fish, which feed eventually things like mosasaurs. So there are few mosasaurs compared to algae, and medium numbers of things in between. The mosasaur food chain is dependent upon the algae and the plankton. If the impact shut out very much sunlight, it would have caused a crash in the production of plankton. And that crash in the production of plankton would have affected everything else up the food chain. And mosasaurs, being at the very top, need large amounts of food in order to stay alive. Even though they are lizards, they appear to have been very active, which means that they had high food requirements. And so, for want of 10 fish, the mosasaurs began to die. And it seems that they did not survive long after the impact. Now, there are many other things that we can look towards as possible investigations into the future. We might ask what other animals, especially in the marine world, were affected by this Cretaceous impact event. Were the plesiosaurs affected? It appears that they were, but it also appears that there were very few of them by the time we get to the Cretaceous deposits. There are no ichthyosaurs in the upper Cretaceous deposits. They appeared to have died earlier in the flood. But other things survived, such as sharks, probably due to the fact that sharks have a very low metabolism and the mosasaurs had a very high one. We also might ask, are there other flood or post-flood events that we can identify as being a single event around the world? This impact left a very characteristic set of materials behind that we find consistently at the top of Cretaceous deposits, at the top of Maastrichtian deposits. Are there others in the fossil record that we can tie so that we can understand when certain things were happening during the flood, or possibly when they were happening in the post-flood world? And will this give us any sort of help in developing or determining a particularly creationist view of biostratigraphy? Much of our studies in biostratigraphy for creation have been based on land animals and what sort of ecologies animals were living in on land that resulted in their specific pattern of burial during Noah's flood. Is there something that we might be able to study better in the marine world as well? And so with this, I am grateful again for the opportunity to speak to you about what it is that the Lord did in helping me learn about some of his great creations, about the opportunity that I had to visit your country and study animals that were first found in the Netherlands. From Mosasaurus hoffmanni to some of my other favorites. I am so pleased and so grateful that I was able to share with you today. May the Lord bless you, and may he bless this conference as it encourages you in understanding better the Lord's creation. God bless.